Okay, yeah, thank you. So yes, Wallenberg is, WASP is Wallenberg Foundation funding AI initiative in Sweden. Okay, I'm based in KTH. So I noticed today there was no discussion on ChatGPT, and this talk will also not have such a discussion. So just to get this clear. Thank you, Luis, for the invitation. So this is, you have been inviting me also to previous integrity workshops. I have been trying to escape, but it has been difficult. So, so this is my introductory slide, very general. So social media appeared, I don't know, 10, 15 years ago, lots of promise to democratize content diversity. Everyone can be information producer, but meantime, several adverse phenomena emerged. So now we talk about polarization, echo chambers, radicalization, misinformation, coordinated campaigns, hate speech, harassment. So lots of bad things are happening. So in my kind of research and in my group, we are focusing mainly on polarization, bias, and echo chambers. So the first bullet here. And one question would be, but is it polarization really a harmful phenomenon? Should I really try to avoid it? And one could argue that no, so that polarization is associated to disagreement, and disagreement is the basis of our democracy. So we really want different opinions to have in our society in order to take decisions. And also, what could be the causes of polarization? So one could argue that it's part of the human nature to have different biases. So we like to have friends that look similar to us, their phenomena like confirmation bias, selective exposure. So we select what kind of content we want to listen and so on. There are group biases. So we feel social identity. We are proud to be in a certain country or in a certain party or in a certain football club and so on, right? So these are kind of causes of polarization. So it's not necessarily a bad phenomenon, but at the same time, when we talk at the context of social media, social networks and so on, we have to acknowledge that there is a certain amount of algorithmic filtering, personalization that takes place on the networks. So I'm from academia, so I don't know really how Facebook or Twitter works, but I can suspect that there is a certain notion of attention economy. So the social media want my attention, want my engagement in order to monetize. And I receive a lot of content that is personalized to me, and it is very opaque. I have no control over what content I receive. So the network make decisions for me most of the time. So this is something that we try to understand and to offer alternatives, perhaps. So in my group and in my work, we are funded by European Commission, the ERC project, and the topic is on polarization, bias, echo chamber on social networks. And this is kind of an outline of the different work we pursue on this topic, so the different research themes, topics that we are addressing. So there are kind of main three research themes or work packages, I could say. So the first is discovery. Can we discover patterns of bias and polarization on social network? So we have done quite a lot of work with sign networks, for instance, which is the topic of the sign networks was the best paper award that was on this conference on wisdom. So, okay, we're not related, but just to say that the general area. And Bruno Ordosgoiti, who was in Integrity maybe 2 years ago, he gave a presentation on sign networks. Another research direction is on exploration. So how can we help user understand better or in a more global way the information landscape? How can they receive more diverse content? How can they explore different viewpoints? So this could be perhaps an attempt to get out of your echo chamber and go against the polarization. And one step further is what kind of mitigation actions you can take. So what kind of recommendations the system can give to the user. So instead of giving recommendations only that of things that you would be potentially interested and potentially be trapped in this echo chamber, can the system can give some recommendations with the goal of diffusing polarization and with the goal of getting out of this echo chamber. So this is kind of the idea. And today I will talk mostly on the latter two research theme, exploration and recommendation. And for this talk, we will be on the mindset of what Cameron Musco was talking. So we have very stylized models, very simple problem formulations. And the reason for that is, okay, because we're in academia, we don't have access to large data set to do A/B testings or things like that. And also we are quite deeply interested on foundational methods and showing some theoretical results and what can we improve about these simpler models before going to think of how we can fine-tune these models to possibly go in some production or whatever. Okay, so I will start with discussing about the second theme, which I call exploration of different viewpoints. And here the idea is we consider an information summarization task. So let's say that I'm searching for information on a polarized topic. For instance, could be something about the COVID-19 vaccination or on climate change. And I want to summarize. So I go to a website, or I could go to Google search, or I could go to Facebook timeline or Twitter timeline and look for this topic. There are hundreds of thousands of available information. So I want to summarize what are the main issues. So I want to collect a small summary of all the available content. And what I want to do is I want to cover the different viewpoints. So I want my summary to be representative of these different points, but also I want to select not too polarized information items. So this is my goal. And okay, we can view this goal in this context of summarizing news articles, but I can have the same goal in a different setting. For instance, when I want to select a committee to push forward an agreement. So in a parliamentary committee, I want to select the members of political parties. So I want them to be representative. I want to select these committee members from all the parties, but I don't want to select perhaps hardcore liners. I want to select people from each party who is moderate and he's willing or she's willing to discuss and to negotiate about this topic. So this is kind of this problem of reconciliation that I'm talking about. Okay, so we formulate this problem as a clustering problem. We consider what I call here clients, so a set of clients and a set of facilities. And these terms sound a bit weird. They come from terminology of clustering and facility location type of problem. So clients are the information items that I want to represent. So all the available documents, and facilities would be the information items that are of high enough, good quality enough, so that they can play the role of representatives. Okay, so if I look at a very standard clustering problem, I'm looking something like the K-means or the
high quality.
Yes, can everyone who is on Zoom to mute themselves? That could be. Yeah, okay, good. Okay, so if I look at this problem as a summarization problem, the first thing that comes to mind is clustering. So formulations like K-median. So I want to find a set of representatives. So this would be a subset of the available facilities. I want to select case as representative, so to minimize this representation cost. So this could be a good kind of summary. Okay, but what about this non-polarization aspect, this reconciliation cost? So what we did with Bruno Ordosgoidi back in 2019 is to consider an additional term that takes into account this reconciliation idea. So here I care not only about the distances of the individual clients to the nearest facility, but also I want the facilities that I select on my community, so these representative items, to be close to each other, so that they are less extreme, they are able to negotiate, they are non-polarizing representation items, and so on. So this is the idea. So this is kind of a new clustering problem that we introduce. So there is lots of work on the classic K-median problem. So what can we say about this problem? So what we did in our work is to show that if we devise a local search algorithm that had a K-factor approximation for that problem and constant factor approximation if the clusters are large enough. So this was this is some kind of evaluation of this idea and demonstration of this idea on a real Twitter data set. And what we are doing here is the following. So lambda is this parameter that controls the representation cost with respect to the reconciliation cost. And this is on a Twitter data set for which I have Twitter users, and I select a subset of those users, the most influential, to be the facility, so the one that I'm going to represent, to use as a representative points. And for every of those points, I compute a polarization score based on some existing method that is by Pablo Barbera. So it's a polarization score. So it's computed by looking at politicians that every person is working and type of how polarizing content they post and so on. So what they observe is that as we increase lambda, so our representation cost increases. So means that all the information items are represented not as well, right, as lambda increases, but the polarization score of the representatives goes down. So by increasing lambda, I select representatives that represent less well all the available content, but they are less polarized in themselves. So this is kind of what we expect by our problem formulation. And what is kind of nice here is that the polarization score are not taken into account when we compute this reconciliation cost. Okay, so this is nice to see. One limitation of our approach, or one kind of theoretical drawback, was that the approximation factor of order K we had in the previous work with Bruno was not very satisfactory. So this year we work with some other colleagues, so Joachim, Kamia, Benedict, and so on, and we are able to obtain a constant factor approximation from this reconciliation problem. So this is a new paper that it will appear in iStats this year. Will be presented in Valencia. Okay, so how we do that? So the idea is to map our reconciliation cost to K facility location for which problem there exists a known constant factor approximation algorithms, and we do that through a reduction, so that for each facility in our set of facilities, we create a new instance where we assign facility location opening cost that depends on this initial facility. We iterate, and then we solve all of these problem instances we create, and we receive the best solution. So we saw that if we have a beta approximation algorithm for facility location problem, then we get a 2 beta for the reconciliation k-median. And for facility location, we have beta to be a constant factor. I think it's something like a 3.5. Okay, so this is nice. So we improve our theoretical result. The main limitation is that this algorithm is expensive. So the algorithm itself, k-facility location, is expensive. And on top of that, we have we have to solve this f times as the number of facilities. So this is expensive. Okay, so then we also saw how we can obtain a faster algorithm by sparsification. And the idea here is that instead of doing this reduction by running this iteration through all the facilities, we sample a set of facilities using adaptive sampling. So if you have seen the paper, like very important seminal paper by Arthur and Sergei Vasilevsky on k-means plus, where you start with one center, you sample another center with distance proportional to the distance and so on. So you do something like that. We also need to adapt this idea a little bit. So then we do the same kind of concept of creating these problem instances, different problem instances, but now it's order of k instead of being order of number of facilities, and we return the best solution. And now we can show that we essentially maintain the similar order of magnitude approximation guarantee, but we can speed up our algorithm because we do less iterations to this, less calls to this facility location problem. Okay, so this is kind of our new result. We are happy. In practice, this is still expensive. In practice, something like the local search that we had from the previous WebConf algorithm would be still competitive. It is faster and it will give more or less similar quality results. Okay. So then I'm going to talk of another work along the similar lines of exploration. So summarizing information so that we take into account different points of view. So here the setting is the following. So we consider that we have a large set of articles of topic of interest. So these are the articles that we want to summarize so that we give to user a more concise view. And we want to select a smaller set of k articles for the user to read on that topic. Okay, so here item selection is formulated as an information utility maximization problem. So essentially, think that you are suggested to read k articles, and as you read, you increase your information utility that you receive by reading those articles. And it is typically this information utility is modeled as a submodular function. And the idea here, a submodular function is a function that has this diminishing returns property. So as when you read the first article, you receive a lot of information. When you read the second, some of the information that you are receiving has already been covered by the previous one. So the utility that you get by reading the second article, given that you have already read the first, is less than what you get if you would read the second article at the first point, right? So this is how we model this information utility on a set of articles. So kind of a standard problem that we want to solve here is this maximizing a submodular function. So this is maximizing your information utility. So you want to select k items from the set of the available items to maximize the information utility. So this is very classic submodular maximization type of problem. And it is known that standard, like if this function is also a monotone, so then standard greedy is more the best you can do. And there are many other variants of submodular maximization problems that rely mostly on greedy strategies or local search strategies. So, okay, so now what we want to do is to build up on this setting of submodularity maximization, but we want to select items to represent different points of view. And let's see an example here. So let's say that I'm interested on a polarized topic, let's say climate change, and there are different points of view, and I want to learn something about these different points of view. So let's assume here that we have two main points of view. So there is the activism, so point of view that really believes or supports that there is climate change is real and we should act now, and challenging this position, thinking that, okay, nothing is going on, there is just fluctuations in the temperature, and we should not really do something. So let's say these are the 2 points of view. So the way I'm going to model that is with 2 functions, each one corresponding to one of these different points of view. So this would be F1 and F2. And for each one of these points of view, I'm going to say that the user who is receiving this information has different patience. So corresponding here to K1 and K2. So for instance, K1 would be how many articles the user is willing to read until their patient is depleted with respect to point of view 1, right? So for example, if you are really an activist and you are support this cause of global climate change, K1 would be fairly small. So you want to the articles related like that favor this point of view, you want them to be very top on your ranking. And then as you go down the list of articles that you are reading, then you are willing also to consume some other articles from different points of view. Okay, so let's assume here that for these 2 different viewpoints, we have these 2 functions, F1, F2, and with budgets K1 equal 2, K2 equal 1. And let's assume also that every correct match increases utility by 1, just to simplify things. So our submodular function, in this case, is just a modular function. Okay. So what is going to happen? So let's say that we take a ranking. So the system returns to us 2 articles, so that the first one is on the favoring this activism point of view. The second article is favoring the challenge point of view. So what would be our total utility? Okay, our total utility is going to be 1. Why? Because we get 1 from the first article, but when we reach our second, our patient has been exhausted. So we don't reach at the second because our patient was 1. So we receive 1 utility point only by the first article. On the other hand, if we saw the articles in reverse order, so first the challenge and then the activism, so then our total utility is 2, right? Why? Because we receive 1 by the first, and then we receive another 1 by the second. Since our patient is 2, we can go here. Okay, so what does this show? Kind of the idea now is that by taking into account these functions that model different points of view and these patient scores, each one with a different patient score. So the problem of selecting a set of items that is of interest to the user is becoming a ranking problem now, because the ranking is important. Okay, and this is the problem we study. So we call it maximizing a submodular ranking. So we're giving a set of items. Our goal is to come up to return a permutation of those items. So this would be the ranking. We define a utility so that the utility score evaluated on a ranking within a budget KI is exactly the utility you receive by the KI first item on this ranking. And our goal is to find the best possible ranking so that you maximize the total utility score over all those different functions that model these points of view. Okay, so this is the problem we study and the problem that we develop algorithms for. Okay, so we saw that this problem, of course, is NP-hard because simple case is when you just have one function, which is just the submodular maximization problem that is NP-hard. We also saw that you cannot do better than approximating this problem within a factor of 1.85. And then we saw that how you can get approximation guarantees with this problem. First, if all the items have a uniform cost, let's say for all the items you put the same effort of consuming or reading, then you can get a two approximation just by applying greedy. If the items have different cost, meaning some items, some articles could be large to read and it will take a lot of time and so on, then you have to do a little bit more work, and then your approximation guarantee is going to be 4, so still a constant. Okay, so maybe I will skip the kind of the idea or like some very proof sketch. Just say that this is work mostly based on the PhD work of my PhD student Guanyi Zhang, and he have also looked at the different variations of this problem, dynamic settings where these functions can arrive at any point, items can arrive at any point, or even if they can be, some of these items could be adversarially deleted and you still have to update your ranking. So lots of interesting results by Guanyi. Okay, and then I'm going to talk a little bit about recommendations and this idea of presenting some recommendations so that you mitigate some of the adverse effects. So the general framework here is that we want to, instead of that, like the usual way to think about recommendations is that the system makes some recommendation to increase the relevance for the user or the serendipity of the user or the happiness of the user. So everything is about the user. But here we want to make some recommendations that we optimize measures, different measures of efficiency on the network, right? So what does this mean? So first of all, what are the recommendations? So if you think of your system as a network, recommendations could be either edges, or they could be different content. So you can say that, okay, for you is I'm going to recommend this type of hashtag or this different type, some post or something like that. And then what does efficiency mean? Again, there is a wide literature. There are many different ideas. So one is what Cameron was talking in the morning. So you want to perhaps make some recommendations that you minimize this polarization score, where polarization is based on the Friedkin-Johnson model, or what he was talking, polarization plus disagreement. You might want to look at diversity. So you want to make sure that users see diverse content. You want to minimize probability of exposed to harmful content. So maybe what we were talking before. So if I have identified that some particular content is hate speech, I might want to minimize probability that the users see that. and different types of network efficiency. So in our work, some kind of ideas that we have explored are inspired by earlier work on viral marketing. So this goes back to this classic paper of Kembe, Kleinberg, and Tardos, where they want to select case seeds to promote some content and hoping that this will create some information cascade, and eventually they want to maximize the number of nodes in the network that will be exposed to this viral content. Okay, so so here we have looked at variations of this idea where we don't really do viral marketing, but we look of ideas, something like diversity of content. For instance, here I assume that for every user, the user sees some content. The content has a political leaning, and I define a diversity score to be somehow related to the range of the political leaning of the content that the user see. So if the user see only articles from New York Times and nothing else, so then diversity is very low. If a user sees content across the spectrum, then diversity would be large. So one of the problem formulations we study was what kind of post recommendations I would like to make the users so that the diversity of the content of the user increases, but also it is likely that as these users interact with the content, like repost or so on, the user, their friends also might see that content. So I care about the diversity in the network, not only that is a direct impact of my recommendations, but also organically through resharing, reposts, and so on. Another formulation we study is what we call balance of exposure of information. So the idea here is that assume that that I have two campaigns on the network. Let's say if you think about COVID-19 vaccination, I could have the pro and the against campaign, and you could imagine that each of these campaigns have their own influences, their own echo chambers, and so on. So what if we would like as many users as possible in the network to be exposed to both campaigns? My goal would be to target a small number of users who are likely to influence other users with a goal of maximizing the number of the users in the end of an information cascade process that are exposed to both of these campaigns. Okay. So this was some of our existing work that just give some pointers. Can I use this? Is this sealed? Another notion of network efficiency is related to distances on the network. So you might have heard about small dwarf phenomenon and 6 degrees of separation and so on. So in general, we care about networks whose distances are small, right? Why is that? Because then there are less barriers to information propagation. It's easier for information to disseminate and so on. Okay, so this is something that we have been doing recently. So one problem that one could consider is how can I add case shortcut edges on a graph so that the graph that I obtain after the edge addition has as small diameter as possible. So kind of eliminating these information bottlenecks on the network. And here, again, we take this very simplistic view, and we assume that when I add an edge, this edge is really added on the network, where in reality, this would be only a recommendation, for instance, a friend recommendation. But we can account for that separately, either by a probabilistic variant version of the problem or the cost version of the problem. So for the moment here, we will assume that we are able to add these edges. Okay, so this is a problem that has been introduced 30 years ago. It's a classic problem. It's NP-hard. There are some works, several follow-ups. So this problem has been studied extensively. So, but what happens? So if we take like a classical algorithm for this problem, so how do they add these edges to reduce the diameter of the graph? So most algorithms have two steps. One step is a clustering step, and then they do what we call, and what I will show you now, a star shortcutting. So the idea is that in the first step, so let's say that I want to add 3 edges to minimize the diameter of my network. So I'm going to take k plus 1, so 4, and I'm going to create 4 clusters of the graph. And the way they do that is in what we call in this k-centered heuristic. So I will take one node, I will find the one that is the furthest away, then another one that is the furthest away from the previous 2, and so on. So I will find k nodes that are far away from each other, and I will cluster the network around these nodes. Okay. And then I will add a star. So I will pick one node as a center, and I will connect all the other nodes. And now the diameter of the network will decrease. Why? Because every node can reach any other node by going to its center, then through the center with 2 more hops can reach any other cluster, and then the distances within the cluster are close to each other. So overall, then you can argue how much the diameter would decrease, and also compared to the optimal. So this is the star shortcutting step, because you really add a star. The drawback of this approach is that it creates a lot of imbalance on the network. So if you had to make these edge additions as recommendations, you assume that you make all of the recommendations to one user in your network, and you'll create a hub. Okay, so this is not practical, it's undesirable, it's not robust. So what we would like to do is to have a robust version of this edge addition problem. So this is the problem we study. So we call it same bounded, how we call it, bounded. Okay. Okay, fine. Okay, but now we have a parameter delta that is the maximum number of edges I'm allowed to add at any given node, right? So this is the classic problem. If I set delta equal 1, then I want to decrease diameter of my network by adding a matching, right? Because this is what delta equal 1 will do. Okay, so this is our results. So what we saw is that now, okay, instead of having a constant factor approximation that I had before, I have a log k approximation in the general case if the graph is connected. And the way that this works is that instead of making this star, now because you have this bounded degree constraint, you have to create a tree. So you still find those clusters, but then you connect them through a tree. And this is the log k. On the other hand, if k is not large enough compared to delta and the number of nodes on the network, when you find these clusters, you know that one of these clusters would be big enough. And then you can create a star from that cluster to the other clusters, but not with a single node, but because there are sufficiently many different nodes there, you can take different nodes and you can and then you can get a constant factor approximation. Okay, and then we also saw that you cannot do better than 4/3. Okay, so this was some small result, kind of a little open problem that we resolved in the case of a path graph. Maybe this is not so much interesting. So maybe this is, okay, this is quite interesting. So this is some experiments by trying different types of methods for reducing the diameter for different types of delta. So delta is, remember again, is the degree constraint. So delta equal 1 give you the matching. So one observation is that increasing delta does not help so much. So with delta equal 1, so starting from a network that has diameter 100, or not 100, this is like the original diameter. So this shows the percentage of reduction. So by adding 1,000 nodes, that is a matching, you can go to 53% reduction. And even if you have larger degree constraint, you can still get the same reduction. So this does not help. So delta equal 1 is sufficient. So this is one observation. The other observation is that our methods, the theoretical methods that we kind of propose in this paper, they are not really the best one. So in fact, you can get much better performance by a greedy, for which these kind of guarantees will not hold. So it's kind of a case of discrepancy, I would say, between theory and practice, that your best theoretical algorithm is not the one that gives you the best performance in practice. And when we talk about 4 approximation guarantee and 2 approximation and so on, in real life, this might be the range of values that you operate might not be significant enough to make a difference. Okay, so maybe that's it. Okay, summary of what I talked today is that, okay, social media create many opportunities for connectivity, diversity, and so on, but also for these adverse effects of polarization, hate speech, and so on. So I talked today about very simple computational problems for information summarization and for some recommendation tasks. I think this is a rich field in the intersection of social media mining, information retrieval, like this information summarization, recommendation system, but we also need to collaborate with social scientists and so on to understand mentality of people, of how they operate on the system and what we really want to do. I think the work we did, I think is interesting in my opinion, but also has some clear limitations. So our models, I think, are mainly mathematical abstractions, and when you go to practice, you would like to fine-tune that. We also make some strong assumptions. For example, when I talk about information utility, I assume that I'm able to assess what is the information utility with respect to a given topic. I assume that I know what would be the patience of this threshold K of a user with respect to a given topic. We think that this could be estimated perhaps from user logs or whatever, but it has not been tested, right? For future directions, I think there is, for some of the results I presented, there is still room for improvement. And also, what I presented is mostly theoretical, so I think it will be very interesting to see how these ideas perform in a real scenario. Okay, and that's it. So many thanks to co-authors, Bruno, Joachim, Kamiar for the reconciliation K-median, Guan Yi and Nikolai for the maximum submodularity, maximization Florians for the diameter, and also over the years, I have worked with many people on this topic. So yeah, that's it.
Thank you, Aris. Any questions not related to ChatGPT? No, the ones on the ChatGPT? No. I have questions. Well, it's more comments, no? Because I noted several times the same thing, which is beyond the theoretical models, which the disclaimers that you put at the end. That's great for an industry person like me. But I missed some of the ideas there have in industry application or social networks, they have like a cost, for example, engagement cost, or I was noting, for example, say that we use the shortcutting example for information flow. Not sure if the Amazon experiments that you had in there had anything to do with polarization, but that in reality is a little impractical, like connecting completely opposite points of view to reduce polarization. That comes at a cost, right? Like as in, hey, I'm going to connect you to, I don't know, somebody from Real Madrid, say something like that. But also in terms of recommendations, this is something that we are looking at in industry all the time, which is the trade-off, right? It's not that we are ignoring completely network efficiency, but what I'm missing in some of the experiments, you didn't go a lot in depth, is that notion of, okay, this is going to come at this trade-off, or can I add like some, for example, watch time, cost associated to the budget that you were talking before, that fatigue, that watch time cost. So all these costs that come like with like all this network efficiency for industry is like really a big problem, right? And yeah, not sure if you've thought about this and if you have any reflection on that. And I know real data sets would help, but if you have any thought on that.
Yes, very good comment. Actually, there are two comments, I think. For the for this idea that you cannot connect everyone to everyone, yes, this is we have thought a lot, and for some of the work we have done, we take this into account explicitly. So we have like every recommendation is also associated with a probability of this recommendation being accepted or a cost. So then you can very easily modify this problem, the simple problems I presented to a probabilistic version of the cost. So you might have a link that is very good, like connects like different communities and so on, but you know that this link has a very low probability of being accepted if you make a recommendation. So then another link would be preferred by the method, even if it is the resulting kind of efficiency would be less, but it is more probable that this will be accepted. So I think this can be incorporated very naturally in the framework. For the other question, I think this is harder, and we have not thought so much on that. I think we have been mostly sweeping this into the rug. So like a very standard answer that I give here is that I say, okay, give to the user more control over the feed. So for instance, include some option for the user. The users can opt in and say, yes, I would like to receive more diverse content. I would like to meet someone from the other side. But I have not really considered a model that study both the network efficiency together with user happiness and user relevance. So I think, yeah, this would be very, very relevant, but also harder. Yeah, I would like to think more about that. Yeah.
That one example of this would be, for example, you were mentioning ranking with patients, like the patients factor. If I understood this right, you were factoring patients and the budgets independently per theme or per like opinion function. When in reality, this might be true, but one way that I would model this is like the total fatigue. So a user has like not infinite time of scrolling, and it might be fatigued after whatever number of opinions, but also in addition to that, there's some like fatigue overall, right? Like the total number of items. I think that potentially in that particular model would be easy to incorporate. Right. But I think this kind of approximations, I think this kind of cost and like that more of a sense of like user behavior, because to the controls point that you were saying, I think in this, at least from my experience, we should, I mean, there's people that use the controls, but in reality, people do not like to use the controls. No? And I would challenge you to think, okay, when is the last time that you click on something on a control? No? And very likely it's going to be never, right? So, but anyway, thank you for that. Yeah.
Yes, I will actually follow up on your comments, which is in that climate change example, you were talking about basically the patience factor, right? And you were saying, well, you have more patience if you had pro comments rather than con comments if you're on one side, right? But then you said to optimize the utility, you put the first item as a con item when you're pro, right? At that point, users also judging the platform itself and say, well, these guys are supporting pro or con. And it is actually more likely that they will walk away. That in that sense, I think the patience isn't a uniform function either. It's actually a function of what you presented them.
I realized that I reverse it. So here, the person who is favoring the challenge point of view so this person here with this patient is mostly a challenger, and in fact this ranking is the one that ranks this first. So this is kind of okay here. And yeah, if you assume that you can learn this for the user, so yeah, I would agree with you that is, and probably with what Luis was saying, that it's difficult to learn those patients. But once you have them, once you have a good estimate on that, I think the problem formulation does the right thing. Yes.
All right. Any other thoughts or questions, comments? One question. So this slide deck is awesome. Many references. So there's like a lot of people are interested. Is this online somewhere, or are you? Yeah, because I think this the deck is really great with the references and everything. It will be really great.